with that, I just want to discuss briefly the future directions. Where is this going? Well, millimeter wave applications in this way and this use in backscatter started in this group with the Vanata architecture. This is where we realized that, aperture matters. If you maintain your apertures as you go up in frequency, you could basically leverage millimeter wave and extend the operation range. So it started there. And from there, we went into powering that we discussed today, communications with multiple systems that we showed with the MMID tags, and with sensing, whether it is the humidity, temperature sensing, or localization, where we can track tags in real time. So where is this going? Well, with powering, there's still a lot to basically discover and research. Well, we're still suffering with rectifiers that basically do not have very good efficiencies at these frequencies. So can we design better rectifiers that enhance the efficiency and thus the range at 4 millimeter wireless power transfer? Can we design higher power amplifiers for these frequencies, for this frequency of operation? For communications, can we work with higher data rates or implement complex modulation schemes or have a lot of tags that are communicating with each other? For sensing, can we play with augmented reality or RFID fusion, which is a topic that I worked on before, for example? Can we implement this for indoor GPS navigation, robotics, etc.? So here I'm gonna let Shayun also discuss some other future directions.
Yeah, thanks, Aline, for the nice presentation. And then in this slides, it also showed in our paper. And when we read the paper, we want to look at how realistically we can implement the wirelessly powered backscatter communication in the practical products or the commercialization for a successful company. And then we pick these two very kind of interesting work in our paper, also in the slides, is made by the Professor Joshua Smith's group from the University of Washington in Seattle. So the one main impression for the backscatter communication is like the backscatter communication is indeed very low cost, low power, but the kind of bottleneck is like they are very low data rate. So typically we'll talk about a few tens kilobits per second. So in this occasion, if you transmit the sensor raw data, it's okay. But if you want to send the image or if you want to transmit the videos, then it becomes problematic because you need more power and more advanced kind of switching and modulation technique. So in this work, the Professor Smith's group, they have demonstrated one work is for the backscatter-based wirelessly powered. One thing is the camera, so they use the modulation based on OFDM, and then they can achieve a 200 kilobits per second data rate. So that was a kind of very high data rate compared to the other low rate backscatters. And another one is even more interesting. They demonstrated a passive mobile phone. So they put all the essential components for a cell phone to receive the audio call, to answer the calls, to receive a text message. Even this phone, although this phone does not have a smartphone display, you cannot show the image, but this phone is entirely powered by the kind of modulated wave from the mobile base station, and then backscatter using the backscatter technology to generate the uplink signal, and then successfully demonstrated a loop for the from cell tower to the end user devices. And the next slides, we will hand over to Professor Manos. So they demonstrated an even more impressive ultra high data rate backscatter applications.
Thank you very much, Oyon. Hello, everybody, from me as well. This is one demonstration of one of the first gigabit per second millimeter wave backscattering structure. This is based on work of Dr. Kimionis, Dr. Georgias, Dr. Daskalakis as well. And you can see the simplicity of the millimeter wave backscatter on the left. Just utilizing some very simple PATS antenna array with 5 elements and a p-hemmed transistor at the bottom, then arranging for the bias or non-bias states to feature gamma equal 1 and gamma equal -1. it was possible to demonstrate a variety of modulation schemes that could improve security, but also increase dramatically the data rate. Here you see 2 gigabit per second. We have seen demonstrations all the way up to 4 gigabit per second, and a variety of modulations ranging from BPSK, QPSK, all the way up to 16 QAM for a very, very simple form factor. I saw one question on chat about the complexity of MMIDs, but you can see here this MMID is extremely simple. You have just a very simple printed patch array on a flexible substrate, just one transistor, and here you go with 2 gigabit per second backscatter with extremely high energy efficiency. You can see something below 0.17 picojoules per bit. This one can be brought down all the way at least to 0.1 picojoules per bit for gigabit per second implementations. Another application we are all spending time nowadays, all co-authors of this paper, is how to apply backscattering now to larger scale structures, such as metasurfaces. There's lots of discussion about smart cities, smart houses, smart agricultures, adding metasurfaces everywhere, and utilize even walls as metasurfaces. So one of the ideas is to harvest or backscatter existing ambient signals such as Wi-Fi, TV signals, LTE, 5G different bands going all the way from 3 to 6 gigahertz all the way up to 40 gigahertz, and enable now metasurfaces that are fully autonomous and that allow the complete elimination of blind spots. So one of the main issues for the practical implementation of smart environments is the existence of blind spots due to blockage, shadowing, and all this. Now, utilizing autonomous metasurfaces, you can eliminate this, and also you can enable high granularity smart skin. Smart skin, including now a multitude of sensors, chemical, gas sensors, not only temperature and humidity that are ubiquitously found, but possibly, for example, chemical VOC sensors or safety sensors that will not require any battery and that could be operating almost continuously utilizing existing signals within your house. And this structure we recently demonstrated in a paper including one PhD student of our team, Meeting Chen, and also Dr. Lynch, Professor Aid, and also Dr. Jimmy, very recently, that we can couple actually backscattering in terms of wireless power transfer and also communication in practical metasurfaces. You can see here some Rothman lens enable MMID type of architectures that could pretty much bypass obstacles from radiation and illuminate RF devices that could be completely blocked otherwise. And this one could find a very significant application for beyond 5G wireless networks of the future. So installing completely passive zero power metasurfaces, redirecting base station signals to previously unreachable areas with a very, very minimal power overhead that can be covered by either energy harvesting or deliberate wireless power transfer. So I would say metasurfaces is another front for backscattering for the future. And before forgetting about this, another important obstacle that backscatterers have to address nowadays is implementation in flexible or curved surfaces. As Professor Aid said before, now we may have to mount these backscatters not in planar surfaces, but around poles or wearables, smart wearables, or complicated 3D surfaces. So we have to make sure that the performance of these backscatters will be pretty much impact-free for a variety of flexing, stretching, and twisted configurations.
Thank you, Professor Manos. I think we can take some questions now.